we could design materials that never crack under pressure? What if we could predict their strength before even making them? Hi, I am Alia Aina. In this video, we explore how scientists can predict how stiff or stretchy a material is by studying its atomic scale features. We will see how advanced simulation reveal the connection between atomic arrangement and mechanical properties like Young modulus. Measuring Young modulus in the lab often involve complex tensile or nano-indentation tests, repeated trials, costly materials, plus many exciting prediction models are too narrow and fail to disorder structure like doped amorphous carbon. Using LAMP software, the research modeled thousands of materials. They heated carbon system to extreme temperatures, rapidly cooled them to form atmosphere structures, and applied tensile forces. This simulation helped determine stress-strain relationship and extract Young modulus from the elastic region of the curve. The x-axis represents strain how much the material stretch, while the y-axis shows stress how much force is applied. In the initial linear region, stress increases proportionally with strain. The slope of this linear region is the Young modulus, denoted as the formula. We see a plot of Young modulus versus coordination number. The trend suggests a general increase in Young modulus with coordination number, but the data points are highly scattered, meaning the coordination number alone is not a reliable predictor. The same data is replotted using effective coordinate number. Now, especially for hydrogen-containing amorphous carbon, the data collapses into tighter, more predictable trend. The vertical axis shows the average Young modulus, while the horizontal axis shows doping ratio from 0% to 20% for different elements. The key insight is oxygen and silicon doping reduce Young modulus, and nitrogen doping increases it. The graph shows how the effective coordination number changes with doping ratio. Interestingly, the coordination number decreased with more oxygen, which aligns with the decrease in Young modulus. However, for nitrogen and silicon, the coordination number remains almost unchanged despite the changes in Young modulus. So, in the conclusion that bond stiffness also plays a major role, not just coordination. This graph displays energy versus bond length for four types of bond: carbon to carbon, carbon to nitrogen, carbon to oxygen, and carbon to silicon. The curves were fitted using a harmonic spring equation. The steeper the curve, the stiffer the bond. The slope gives us bond stiffness, and the fitted values show carbon-nitrogen is the stiffest and carbon-silicon is the least stiffest. These values explain the trends seen early. Nitrogen doping makes the material stiffer, while silicon reduces its stiffness. Even its coordination number stays the same. We see data from doped atmosphere's carbon plotted against this new combined variable. The scatter we saw earlier is now gone. The data forms a tight linear trend with a very high R-square value of 0.96. This model is tested on a wide variety of materials including silicon oxide, silicon nitride, and silicon nitride oxide. Hollow points are from simulations, while solid points are from experiments. The model still holds strong with R-square equal to 0.92. This model empowers research to predict stiffness using only atomic composition and structure. It enables faster, more cost-effective materials development and opens doors to innovation in electronics, aerospace, and beyond. In conclusion, this work provides a powerful theoretical model to predict Young model from atomic level data. By introducing two novel parameters, the model bridges the gap between structure and mechanical performance. It works well for amorphous and subcrystalline covalent materials, though improvements are still needed for metals or highly anisotropic crystal. This approach has great potential for cost-effective material design and non-destructive testing in the future. Thanks for joining me on this atomic journey. With every bond we understand, we get closer to engineering the materials of the future.